okay, relative to lambda 1, the second eigenvector relative to lambda 2, and the third one. Now I can diagonalize A simply by multiplying, this is the P matrix, okay, times the diagonal matrix times B minus 1, and this is gonna equal to A. Or as I did, I can get the diagonal matrix equal to P minus 1 times A times B. Are you with me, Muhammad? Okay, this is perfect. How to explain A as a diagonizable, as a multiplication of a diagonal matrix, and how, even so, how to get the diagonal matrix relative to the main matrices. Eigenvectors from distinct eigenvalues are linearly independent. This is really a very remarkable remark. Eigenvectors from distinct eigenvalues are linearly independent. Also, an n by n matrix with n distinct eigenvalues is diagonizable. There is no question about this. If an n by n matrix has n eigenvalues, all distinct or not, okay? For an n by n matrix A, the following statements are equivalent to each other. If A is diagonizable, it's exactly like A has n linearly independent eigenvectors. The sum of the geometric multiplicities of the eigenvalues of A is equal to n. If you remark in the previous example, if I added the geometric multiplicity of each vector, it will come to 3. This is 1 plus 1 plus 1, which is equal to 3. Okay? Similar matrices have the same eigenvalues. Also, for those propositions, remark, for an n by n matrix, the sum of the eigenvalues of A is equal to the trace of A. What's the trace? The sum. Yes, the sum of the principal diagonal. Remark, that's the problem, that's the matrix of the previous problem. Add 4 plus 2, which is 6. 6 minus 3 is going to come up to 3. So I'm adding them. So once more, the sum of the eigenvalues. If I added the eigenvalues that I have, 1, negative 1, and 3, the sum also will equal to 3. So that's the first one.
دي ممكن استعملها لو جاب لي سؤال MCQ.
Yes. Yes. Yes, exactly right. The product of the eigenvalues of A is equal to the determinant of A. So if I multiply 1 times negative 1 times 3, it's going to equal to the determinant of this matrix. Multiplying 4, 2 times negative 3, 2, 1 plus negative 7, 1, 3 plus 2, and so on. Continue, it will equal to 2. The geometric multiplicity of each eigenvalue is not larger than the algebraic multiplicity. And that's a very good remark, you should keep in mind. Also, if each row of A sums to K, that's a very nice remark. That's a very nice remark, this remark. Okay, once more. If each row of A sums to a certain number, then this number is an eigenvalue of A. That will make your life much easier. Okay? Associated to the eigenvector of ones, this is 1, 1, 1, 1, 1. So I can get one of the eigenvector values very quickly if the sum, okay, of the rows is equal to certain number. Usually this certain number will be an eigenvalue. The same will go for the columns if you make the addition, but you are not sure, it's not associated, or it's not necessary to have ones as a vector, an eigenvector. Okay, let's remark this situation. If you look to this matrix, which is 10, negative 1, negative 3, and so on, if I added the elements of the first row, it's going to come up to 6. The elements of the second row is going to come up to 6. The elements of the last row is equal to 6. Now I know that one of the eigenvalues is 6. Okay, it's going to come up to 6. This will make your life much easier in evaluation because you know already one of the values. Okay, so you will be able to get the result. And once the sums of these values is equal to a certain quantity, you will be able, okay, to evaluate the values. If I've tried to expand this equation, I have one of the lambdas equal to 6. So I've ended up having this characteristic equation. So lambda is equal to 0 and the lambda is equal to positive 6, and it is repeated 2 times. Here the algebraic multiplicity of eigenvalue 6 is 2. Now I will go. noticing that as A two equal rows. خلي بالك ان انا هنا برضو انا حسبت بس ما خدتش بالي من المعلومه دي. In الفيرست row والثيرد row they are identical. In this case, this matrix is not going to be diagonizable. And you will have two values of eigenvalues equal to each other. So A as a two equal rows, meaning that A is not invertible. A is not going to be invertible. And lambda 1 is equal to 0 is an eigenvalue of A. Now I know that 6 is an eigenvalue and 0 is an eigenvalue of this matrix. All rows of A is add to 6, meaning that lambda 2 is equal to 6. A is a 3 by 3 matrix, so it has 3 eigenvalues. Remark, if I added the values 10 plus 5 plus negative 3, it's going to be 12. I know that one of the eigenvalues is 6, the second eigenvalue is 0, so if you give 12 minus 6, you will have the third one, which is 6. Okay, so the trace is equal to minus 12 as I told you, and so I can speculate the value of the third eigenvector, and that's a very nice problem. You can have it with the alternatives. Part number 2, the eigenvalues of A are 0 with algebraic multiplicity of 1 and 6 with algebraic multiplicity number 2. If I try to get the eigenvalues relative to 6, I will start substituting in the main equation by lambdas equal to 6. And in this case, I ended up having this guy here after reaching the reduced echelon form, which means the first component is equal to the third component, the second component is equal to the third component, and the span is 1, 1, 1. And this is exactly from the remarks that we saw, that I told you in the previous proposition. Remark that the algebraic multiplicity for 6 is 2, while the geometric multiplicity of 6 is just only one vector. They are not equal to each other, so it's not a diagonizable matrix. The geometric multiplicity of 6 is 1, and the algebraic is 2, so different from the algebraic multiplicity, so A is not diagonizable. Okay? Okay, also this bunch of propositions is really very interesting. That if A is singular, if and only if, 0 is an eigenvector of A, so it's going to be a singular matrix. If lambda is an eigenvalue of A and V is a corresponding eigenvector, then lambda k is an eigenvalue of the matrix A to the power of k, and V is a corresponding eigenvector, with k is a natural number. A and the A transpose have the same eigenvalues. Remark. Okay, A and B and B and A have the same eigenvalues. So if I have two matrices, A times B and B times A, they will have the same eigenvalues. Okay, these are really very important remarks as I told you. Now for the exercises, we have finished the eigenvalues and the eigenvectors. You will find the first bunch of problems are really very direct. He's asking you find their eigenvalues and respective algebraic and geometric multiplicity. So all I have to do is to try to solve these equations. Just also check if you can add the numbers and the value of the rows, if it's gonna sum up to a certain value or not. So for the first problem, if you try, you will have 0, 1, and 3. Those are the eigenvalues. The geometric multiplicities are 1 and the algebraic multiplicity are 1, so it's diagonizable. For the second matrix B, you will have 2 and 8. Those are the eigenvalues. The algebraic multiplicity 2 is going to be repeated 2 times. 8 is 1 time. And for the geometric multiplicity, it's going to be 2 and 1, so it's also diagonizable. And for the last one, it's not going to be diagonizable. As you can see, one of the eigenvalues has an algebraic and geometric multiplicity different than each other, so it's not diagonizable. This is also a very nice problem. Show that 2 is an eigenvector of A and the basis of its associated eigenvalue. I can, of course, get A minus 2i in order to know if 2 is one of its eigenvalues. I will just do a quick check, doing A minus 2 of an I. So that's the matrix. I will subtract 2 from the elements of the principal diagonal, and then I will try to reach it. So it is already, and then solve a minus 2i is equal to 6 to get the corresponding eigenvalue. Now I can get the eigenvector, that's the eigenvector. If you remark, 2 is just only a number, one of the eigenvalues, that's the corresponding eigenvector. To answer the second question, if this matrix is diagonizable or not, I need to be sure about the algebraic multiplicity. I know that the geometric multiplicity is equal to 1. But if you remark for this matrix, you will have 2, 2 and 2. And those are repeated values. And if you try to expand this determinant, you will end up having an algebraic multiplicity of 2, which is gonna be 3, I believe. And so the algebraic multiplicity is gonna equal to the geometric multiplicity, and this matrix is not gonna be diagonizable. By the end of this problem, we come to the end of this slides. I believe I sent you the slides on the WhatsApp, and also you can find them and the video on Moodle, so you will be in a very good shape. Next time, inshallah, if I get time, I will try to solve more problems with you. Please do the assignments. Next time, we will have to finish the assignments, have to be printed and to be with you, and we will try to finish them within our tutorial, inshallah. And I will go for the dynamical systems. Thank you very much. I will see you next time. Thank you.
زي ما بقولت يا دكتور اللي هو ويك 9 صح كده؟
إيه.
ويك 10